Today, we're very pleased to have Barton Zwiebach from MIT here. He got his PhD from Caltech and did postdocs at UC Berkeley and MIT, and now is a professor at MIT. He is well known for his work on string field theory, D-branes with exceptional symmetry, and tachyon condensation. And he's here for a few weeks teaching a Psi course. So thank you, Barton.
Thank you. Great. It's a pleasure to be here on a longer-term visit and enjoy the good questions of the PSI students and talking to so many friends here. And what I would like to talk to you about today is a question that is in everybody's mind when they think about string theory and gravity. Somehow, there's something about gravity in string theory that makes it work, at least much better quantum mechanically than Einstein's theory of gravity. And finding what that thing is probably a kind of question that has to be approached from many directions. I'm going to show you one direction in which we've been thinking that probably has some import on this question. So let me begin by just setting the terms of the discussion and remind you a little what string theory is. String theory, in its second incarnation in the 80s, tried to be a theory of all interactions. And that's, in many ways, the ultimate goal of string theory. Although these days, it turns out that the applications seem to dominate quite a bit the field. There are applications to heavy ion physics, now to condensed matter physics. There's always been applications to mathematics, and all kinds of other ideas. So the main thing about string theory is that it appears to be a consistent quantum theory. And moreover, that string, that dynamical system, contains always a mode of excitation that is identified with a graviton. So being a quantum theory and containing a graviton is a really remarkable thing. It also contains other things like gauge fields, fermions, all kinds of nice things. As far as we can tell, this theory describes gravity consistently and therefore consistently with quantum mechanics. This is not at the level of a mathematical proof, but there's all lines of evidence in that direction. So in this way, string theory addresses one of the most important conceptual problems in physics, the basic incompatibility of quantum mechanics and relativity. The obvious question for string theorists is how do we get rid of this incompatibility? And again, string theory is not what one would say perfectly and fully formulated. Certainly, there's not the equivalence of this Einstein-Lagrangian, which is so lovely. So one thing that seems clear is that string theory doesn't seem to change the rule of quantum mechanics. String theory, on the other hand, does seem to change Einstein's gravity. And how does it do so? So as I mentioned, there's probably many ways to try to discuss this. There's a top-down approach. You could say we have Einstein's field theory. Well, what is the string field theory? And that must be what it is and how it looks. So just like Einstein's theory is a field theory for a gravity field, you can introduce fields of strings and write corresponding open and closed string field theories. And these string field theories have enormous sets of symmetries, gauge symmetries that are incomparably larger than the ones we're familiar with. And they include the symmetries of Einstein's theory, although you can't quite prove they're exactly the same. They look the same to first approximation, but maybe they're modified in some subtle way in string theory. Now, moreover, if you just want to understand gravity, that's not the most natural question in string theory, because string theory contains an infinite number of modes, and isolating one and asking questions about one without trying to consider the other ones is not an obvious the good strategy. So it's not so easy to disentangle gravity from all the other fields of the string, and that has made it difficult to answer precisely what is different about gravity. But one can do something if you're willing to work hard, and we've been trying to do that in the last few years. Another way in which you can try to understand what's different about gravity is if you study black holes. And there's been a lot of work and done that in trying to understand the origin, the microscopic origin of black hole entropy and all kinds of nice things. And that could be perfectly the subject of another colloquium in which somebody says, look, I'm going to show you what's different about gravity by looking at black holes. Or yet another marvelous direction is this ADS-CFT correspondence, where gravity in certain backgrounds is just not gravity, string theory in certain backgrounds is completely equivalent to a field theory. And therefore, since string theory contains gravity, this is surprising that by the time gravity is supplemented with other things, it can sometimes become like a field theory. So this would be yet another way in which you could have a whole colloquium. The way I'm going to try to do this is by just asking, what would you do different from Riemann if you would want to do string theory geometry properly? What must be changed? And interestingly, there's really good things we can say and some observations that have come to light that show what may happen to the ideas of Riemann that were so crucial to gravity. So Riemann is really a hero for many of us because he invented Riemannian geometry, and that's the Riemann tensor with its 4 indices. It's a remarkable extension of what Gauss did of understanding the intrinsic geometry of two-dimensional surfaces. And as a side, this Riemann also did the Riemann surfaces, which is the whole theory of complex two-dimensional manifolds, which are the surfaces traced by strings. So if you're doing string theory gravity, by the time when you're working with the string, you're using Riemann surfaces, and by the time you're working with the space-time, you use Riemannian geometry. So this person sort of did it all. This Riemann curvature that I showed there helps you decide if a space is flat. The Riemann curvature tensor has a lot of information. And therefore, having 4 indices, people construct contractions of it. One of them is the Ricci curvature with 2 indices, and the other is the scalar curvature. They contain less and less information than Riemann. A space with that is Ricci flat need not be flat. They can have a Riemann. But these are also important objects because, in fact, Einstein's theory, the Lagrangian, is written just using, to 0th order, the curvature scalar, and the field equations use the Ricci tensor. They don't use the Riemann tensor. Well, the right mathematical language to describe string theory is not known. And I suspect in some way this is going to take a while to totally figure it out. In the middle 90s, a suggestive extension of geometry called generalized geometry was developed. Basically, it's the work of Hitching, the person to the right, and his PhD student Gualtieri, Marco Gualtieri, who's a professor at the University of Toronto now. Those were people that did much of the work, and there's another person from Berkeley, student of Einstein, a mathematician. His name is Courant. This is not the Courant of the book Courant and Hilbert, but it's a younger Courant, and he invented a tool that is very important that we're going to talk about today. So it was plausible, and in fact, many people found out that some aspects of this geometry, generalized geometry, are natural for string theory gravity. So that's it. You know, generalized geometry is really, after all, a mild generalization of geometry, very mild one. What I'm going to talk about is a little generalization of generalized geometry in a sense. So what I want to say is that the relevance of generalized geometry became clear with some recent work that we've been doing on something called double field theory, which is in some way a small extension of the ideas of generalized geometry. It's a little epsilon, but you know, each time you change these things by a little epsilon, a lot can happen. You know, it's very hard to start with Riemann and change everything at once. We change a little bit things, and already things are very non-trivial and they're different. So it's enough. Double geometry started, actually, double field theory is a subject that many people tried to work on. Zeitlin was one of the first ones. Warren Siegel, who is at Stony Brook, did a lot of very interesting work on this, and it largely went unnoticed, unfortunately, because it was not, it didn't end up making the connection with familiar ideas, so it looked like something cooked up. In its modern incarnation that started around 3 years ago, in 2009, oops, there's no, my wife is calling me. Wish me good luck in the colloquium, probably. Let's begin, therefore, this story. We'll talk about the work that has been done in this double field theory, and it's related to the T-duality properties of closed string theory. So T-duality is the key idea. It's one property that we'll discuss now that is peculiar to strings and has something to tell us about this story. So I want to make a disclaimer. I said today this talk was going to be about the difference between Einstein's gravity and string gravity. And you would have all the right to believe that I was going to tell you perhaps about experimental differences between the two. That I can't do. It's possible that that will happen, and ideally it should happen in not too far away future, but this is not our subject. Our subject is just taking that theory that seems to do some things right, like producing finite amplitudes and having all kinds of other remarkable properties, and figure out what's different in geometry and what must be changed in that way. So let me tell you about gravity in string theory. The first thing that is really characteristic of gravity of string theory is that it doesn't come alone at the massless level. You can do in field theory gravity just alone, but in string theory you can't do that. In string theory, in addition to the symmetric gravity field, there is antisymmetric tensor field, the Kalb-Ramond field. So this is the Einstein's theory, Lagrangian, the scalar curvature. So there's a massless field, the graviton, that is symmetric, and there's an antisymmetric field, and there's a dilaton field. 3 massless fields, and they are all crucial to the structure of string theory. So in a sense, string theory, talking about gravity, is okay, but you really cannot escape the fact that in every string theory, pretty much, there's always these other 2 fields, the antisymmetric tensor and the dilaton. So what are they? What is the role of Bij? I want to just give you a little intuition why it's always there. And for that, I want to remind you of Maxwell's action. And Maxwell's action for the coupling of a point particle to a gauge field. So suppose you have a particle moving, that's the trajectory gamma, and you have a gauge field all over space-time, AI of x. The coupling of the particle to the electromagnetic field is written by that action that we see there, S equal Q over C integral of A dx, written with the help of a parameter, reads like the last equation. The parameter is tau. And this is the kind of action that one writes for the mechanics of a particle that has charge. This action is actually Lorentz invariant. The I index is properly contracted. This gauge invariant under gauge transformations of the vector field, AI. Those transformations, delta AI in red equal DI epsilon. If you try to see that that's a gauge invariant, you will find that it becomes a total derivative over the world line. And you throw away the terms assuming that they vanish at infinity. Finally, it's reparameterization invariant. The parameter that you use is not relevant. Actually, this is the kind of thing we've been teaching in the Psi course in the last week. So what happens for a string? For a string, there can be a string moving in space-time, and there are ambient fields on the world, not only on the string, but all over the world. There's a metric tensor and an antisymmetric tensor. And the string feels them. And it actually, the action for the string, you can write a term very analogous to the one we had before, where we integrated the tangent vector to the world sheet times the gauge field. You made that Lorentz product. Here, you have two tangent vectors on the world sheet, one along the string and one around time on the string. So you have two tangent vectors you can integrate against something with two indices as shown there. That's the Bij, the Kalb-Ramond field. So that's a coupling, and we call it an electric coupling, in which the particle feels this time the string feels the Kalb-Ramond field. This coupling is Lorentz invariant. The Ij indices are properly constructed. Gauge invariant under that transformation. That takes a little work to check. And it's also reparameterization invariant. You can change tau and sigma, and this doesn't change. And that uses the antisymmetry of the field, Bij. Those are all short calculations, but they're not totally trivial. If you don't see how they work immediately, you would see it after a few minutes calculation. The result is that if you ask, why is there a Bij, it's because that's like the Maxwell field for an extended object. The strings are electrically charged under Bij. There is that coupling. The strings generate the Bij field. There are sources for the Bij field in the same way as a charged particle is a source for the electromagnetic field. So that's the reason for being for this field, and that's a good intuition to have. Finally, the last universal field in string theory is something called the dilaton. That's a scalar, a massless scalar field. If you're trying to do a model that reproduces the real world with the dilaton somehow has to acquire a mass, and that can be arranged in some phenomenological models from string theory. A curious thing about this coupling constant is that its expectation value, as given by exponential of -2 times the value of the dilaton, is actually proportional to the 1 over the string coupling. So the coupling constant of string theory, the strength of interactions, is not a number that you can put by hand, but rather it's a field in some sense that you can have parts of the universe that are at strong coupling, parts that are at weak coupling. If the dilaton is constant all over space-time, the same coupling holds everywhere. So that's another massless field, and that's the last actor in this field. Now, with these three fields, the low energy action of string theory is the following in that box. S star, it has the exponential of the dilaton. There's the Einstein term, R. There's the dilaton kinetic term, and then there is a kinetic term for the Calvert-Ramond field, this h squared, where h is the field strength associated to this 2-index field. Just like F mu nu is the field strength associated to the gauge field with 2 indices, if you have a gauge field now that has 2 indices like Bij, its field strength has 3 indices. This theory is the low energy theory of the fields that are present and has a set of symmetries, as you would expect. So it has a symmetry of diffeomorphism. These are coordinate transformations, and it's characterized with a psi with an index up. There's no need to erase, but it comes from diffeomorphism, so delta x I equals psi I of x. From there it comes, and you also have B gauge transformations. We talked about the gauge invariance that is in red there with a parameter psi tilde with an index down. So that's the gauge invariance of the B field. And therefore, there's the psi tilde gauge parameters. So there's a psi I and there's a psi tilde with an index down of x. And people say, well, this is a contravariant vector, and this is a covariant vector, or this is a vector, and this is a one form. They're matched to each other. There's a nice relation, and that's going to be exploited. Basically, you're going to try to make those symmetries indistinguishable. So let me write the gauge transformations. They're fairly in mathematical language. You don't need to worry too much really what the precise formulas are, but let me write them the way conceptually are understood. So the metric, the G field, and there's these equations in red there, the G and B transformations are given by, for diffeomorphisms, this L psi. Those means Lie derivatives. Lie derivatives are the kind of derivatives that are needed for diffeomorphisms. So we have L psi of G, L psi of B. Now the other gauge transformations, the B gauge transformations with psi tilde, appear as the exterior derivative of psi tilde. Because B is a 2-form, psi tilde is a 1-form, it's an index down, so that's how it works. So these are the gauge transformations. This is not generalized geometry or anything more than what we all know, written in an elegant language. Now you can ask, what is the algebra of gauge transformations? And we sort of put these things together. This is the beginning of generalized geometry, is saying, look, let's add these objects. Like add these vector spaces where these things live on. So the general parameter is going to be called psi plus psi tilde. And we recognize some things are vectors, some things are one form, but we treat them together. So if you want to consider the algebra of gauge transformations that you have there, you do one gauge transformation with a parameter psi1. I think it would have been better if that equation read on the left hand, delta psi1 and delta psi2. And here these psi's represent the whole thing, the vector part of the parameters and the one-form parts of the parameters. So the commutator of two of them is another transformation where the vector part of the transformation is given by the Lie bracket psi1 with psi2. And the one form of the gauge parameter, the B field gauge transformation, is given by these Lie derivatives of those one forms that you see there in the second equation from the bottom. So in here, in the above equation, we have the Lie bracket. That's another important construction in mathematics. If you have two vector fields, the Lie bracket gives you another vector field. Now, Having said all this, we're going to talk about this duality called T-duality. So it's another of those dualities that exist in string theory. Nowadays, ADS-CFT is very popular since the middle 1990s, but T-duality certainly dominated the previous 15 years and continues to puzzle us. So what is it? What is T-duality? So you imagine a closed string, and you try to consider what happens if that closed string lives in a space that has a compact dimension. One of the spatial dimensions really makes a circle. And then the closed strings that move in this space will have peculiar behavior. So here it is, a closed curled up in a circle of radius r, which we write as x is similar to x plus 2 pi r. And the closed string is described with a parameter. As you move, change the parameter, you go or travel around the string. That parameter is called sigma and runs from 0 to 2 pi. A typical closed string is described by superposition of modes. So x of tau and sigma. Tau is a parameter related to time evolution, can be chosen to be time in some gauges. There's reparametrization invariant, so you can choose it pretty much to be whatever is physically reasonable. And there we show a little closed string moving along this sort of compact dimension. I've added along with the x direction, a y direction, so the compact dimension now looks like a cylinder where we can draw strings better. And there it is. It's a closed string that is moving, and its mode expansion is up there. In the quantum theory, everything becomes an operator. The x on the left-hand side is the x0. The p is a momentum, the xn's. And x0 with p form a canonical pair. These are the momenta and the center of mass coordinate of the string. So x0 commutator with p is I. Now you're moving on a circle. On a circle, the momentum must be quantized. Any wave function that exists in a circle must have quantum momentum that is quantized so that the wave functions are periodic. The quantization fixes the eigenvalues, and those eigenvalues are, there's a blob there that doesn't allow you to read, but the eigenvalues are n over r, inverse proportional to the radius, where n is an integer, and the momentum p for a free closed string is conserved. Now, a closed string can also wrap. And you have there the closed string, and now I produced a mode expansion where the string wraps around the circle. It's very different from a little closed string that is just running around the circle. This closed string is wrapping around the circle as well. And I've shown a few wrapping strings, and they're topologically inequivalent. You cannot transform one to the other unless you break the string. You cannot either transform one of those little strings that was just going around the circle into one that is wrapped, unless there's an interaction. So in the quantum theory, there's an expansion there, in fact, the top equation, and there's a term in the expansion of the string that is proportional to sigma. This is a term that when sigma goes from 0 to 2 pi, this alpha prime w times sigma must change by a multiple of 2 pi r in order for the string to be well-defined, because 2 pi r means that you've returned to the same point back. So as you go from sigma equals 0 to 2 pi, x changes, but the only thing that can change is by a multiple of the radius, 2 pi r. So there it is. That requires, in fact, that this alpha prime omega sigma be equal to a multiple mr sigma, so that when sigma is equal to 2 pi, you have 2 pi r times m. And that quantizes the w's. The w's must be of the form mr over alpha prime, or m over alpha prime r. Alpha prime is a constant in string theory with units of length squared. So alpha prime over r is a distance. And therefore, if you remember our previous slide, where the momentum is quantized of units of n over a distance, r. The winding is quantized in units of m over this alpha prime over r. And in this, it is as if the radius for the winding was alpha prime over the radius. In the quantum theory, this W is conserved. The winding is conserved, just like the momentum is conserved. For the momentum P, there was a canonical conjugate X. For the winding, there's no such thing at first sight. So we must introduce a dual coordinate Q0 that is dual to the momentum called winding that is conserved. This is not speculative. This is really a proper quantization of the strength. Shows that you must introduce another zero-mode coordinate whose commutator is I. Then the mass of a string as seen by an observer below is, this observer that lives in an open universe, one dimension has been compactified. That observer sees a mass that is proportional to P squared plus W squared, which are given by those values. And since P and W can take any values, this N and M can take any integer values, then this mass formula is invariant under the exchange of R for alpha prime over R. So the spectrum of the theory cannot tell the difference between a radius R and a radius alpha prime over R. And in fact, when people looked at this more, they found out there was nothing in string theory that could notice the difference between those two universes. One where the extra dimension is R, one in which the extra dimension is alpha prime over R, and this was called T-duality. And it's a large departure from Einstein's theory, because in Einstein's theory, you believe that you can tell the difference between an ultramicroscopic distance and a cosmological distance. Nevertheless, in string theory, the concept of geometry apparently is very different, and that's why we focused on T-duality. Now, we need to describe this a little better. But before we do that, let's notice that what has happened. We had a circle, we had the momentum, and therefore an x0 associated to it. If that would have been a particle, that would have been it. But you have a string, so there's a winding that is also conserved, and a dual coordinate associated to winding. So the circle has been doubled. You have an x0 circle and a q0 circle. And they have inverse radiuses. Now, we need to describe this symmetry, this T-duality symmetry, more mathematically to make progress formally. So this is all for T-duality when you have one circle. But if you compactify several dimensions on circles, the T-dualities become even more interesting and more things that you can do. So if we curl up these spatial coordinates, we should supplement the spatial coordinates xi by coordinates xi tilde. And notice the original coordinates were born with xi because the momentum had an index down. The new coordinates come with winding that has an index up, and these new coordinates come with an index down. It's again this interplay that is showing all over. That is important as well. So the circles, suppose you have lots of circles, you can say, all right, let me describe the circles using a metric. Because since distances can be written as ds squared gij dxi dxj, a circle can be described by saying, yes, the x's are coordinates without units, and we're declared that their parameter range is from 0 to 2 pi, all the coordinates. And then the value of the metric, since it's multiplied by dxi dxj, tells you the radius of the circle. So if you put this gij equal to ra squared delta ij, you're describing a set of circles, each with radius r1, r2, r3, r4. And then you could even turn each circle into its inverse. And you would view that as having changed the value of the metric. So one way to say that you've changed a small circle to a large circle is to say you've changed the metric. Additional dualities can be obtained by changing the Kalb-Ramond field. You would not be surprised that the Kalb-Ramond field comes along. And that's the crucial thing about this complete set of T-dualities that we will just describe, is that they transform the metric and the B field, and in some cases they even transform the metric into the parts of the B field and the B field into parts of the metric. They mix them completely. The representations of the action of T-duality mix the metric and the B field. Earlier attempts to do, people have tried in the past. They notice, of course, if you have Gij and Bij, you could add them and you would have a general matrix that is not symmetric. And they've tried to do non-symmetric gravity. But in a sense, unless you put something in, it's very difficult to see what you're doing because diffeomorphisms don't mix these two. General coordinate invariance doesn't mix this and that. T-duality does. And therefore, T-duality is a key symmetry to understand why the metric and the B field, in a sense, form a bigger object that is interesting. So these are complicated transformations depending on what language you use, but they're nicely described in terms of something called a generalized metric. And this generalized metric is a 2D by 2D symmetric matrix constructed as a function of G and B. So you take your metric, you take your Kalb-Ramond field, and you build a larger 2D times 2D, D is the space-time dimension, matrix. And it is symmetric. This matrix, in mathematics, it was called the generalized metric, but actually it was discovered in physics first, and it appears in the string Hamiltonian, in the closed string Hamiltonian. When you compactify a theory, that has been out there since the 80s, and generalized geometry is really a 90s thing. Anyway, this metric was also important for the mathematicians, probably for similar reasons. But what happens is the following. While a T-duality changes a metric G and B to some complicated, G and B changes it to some rather complicated G prime and B prime by doing very complicated mixings, the T-duality acts tensorially and very nice on the generalized metric. Now, this generalized metric HMN, I've introduced indices there that are 2D, take 2D values, HMN. This matrix naturally runs over 2D values because it's double the size of a normal D by D matrix. And those indices are going to be important for us. So what do the dualities do? Well, actually, that's that formula in red. When you apply a duality, it's equivalent to changing the original generalized matrix H of G and B into that H of G prime and B prime, which is given by the action on a matrix of a little h from the left and a little h from the right with a transpose. So that's a new matrix. What is that matrix? That little h is a 2D by 2D matrix that is a ODD group element. So it's an ODD transformation of the generalized metric. And what is an ODD group element? Well, an ODD group element is defined by the kind of elements that leave invariant a metric eta Mn, which is called the ODD metric. So those are the matrices that leave such metric eta invariant. So, you know what's happened here is that suddenly we've gone from G and B and we seem to have encountered two new objects. A generalized metric that encodes this and a flat metric that seems to be relevant to this whole geometry because it's the ODD symmetry. So this T-duality, so at the end of the day, T-duality that began by a humble change of radius to 1 over radius has become this large group of symmetries. And mathematically or geometrically, there's 2 metrics now in this game. Now, I should say one more thing about this generalized metric. It's a constraint matrix, and you see it there. You can raise its indices with the flat metric, as defined there. You begin with the one with 2 down indices, and you raise them with the flat metric. And then it turns out that that object that you obtained is the inverse of the one with lower indices. That is a constraint on the theory, because on the H. But it's a constraint that is satisfied by the formula that I wrote above. You do the calculation, and it works out. Now, it's not surprising that this generalized metric satisfies a constraint, because the general symmetric 2 by 2, 2D by 2D matrix has more degrees of freedom than that of a general D by D matrix, which is G plus B together. There are more degrees of freedom in a symmetric 2D by 2D than in an arbitrary D by D matrix, so it satisfies a constraint. All right, so we know now everything about this thing, so we can do double field theory. So we're going to try to display those symmetries, where our goal is really not terribly ambitious to begin with. It's basically manage to display the duality symmetry of the theory manifestly. In Einstein's theory, or the Lagrangian that we've written, is not manifest. So what we're going to do is take the inspiration from what we've seen, and we are going to have double coordinates. But the double coordinates, xi and xi tilde now, fit perfectly into an ODD index object, x super m. All these indices that run over 2D values are ODD indices now. And the xm is over there. It contains it's a 2D column vector. And the dualities, which are the little h elements, can act naturally on the coordinates, and that's a good way of thinking of dualities. So the fields are going to depend on all the x coordinates. So phi's are going to depend on the double coordinates. And the action is going to be displayed with double coordinates to display the ODD symmetry. So the fields now will depend on double coordinates. Now, closed strings, there's something very subtle about closed strings, and it's an annoying thing, but it's really what defines it, is that you really cannot pick out a special point in a closed string. There's no rule to pick up a special point. In open strings, there are 2 special points, the endpoints. But in a closed string, there's no special point. And somehow this implies a mathematical constraint that can't quite be solved when you look at the spectrum. So you have to impose it as a constraint. You cannot solve it. You impose it all the times. And this constraint, actually, by the time you look at double field theory, which is this theory, requires that this particular Laplacian, partial m, should annihilate all fields. That doesn't mean that the fields don't depend on the extra coordinates, but that puts a constraint on them. And that's a constraint that is you see, maybe this arrow there is a little non-obvious. Remember the metric in the MDM. The M is really the M, the P, eta MP. And eta, if you remember, was 0, 1, 1, 0. So it mixes things. So the D's have some partial i's, the normal ones, and the tilde i's, derivatives with respect to the other coordinates. So this mixes them, and that's how you get the right equation, that you get this kind of Laplacian. If you also demand with a duality, this is a duality covariant constraint. The indices work right. So you're not destroying T-duality by putting this constraint and by requiring that all products of fields are killed by this constraint, and the construction is therefore still possible with T-duality. By the time you require that all fields and all products of fields are killed by this, you have put enough constraints that this theory doesn't have more degrees of freedom or unexpected degrees of freedom. And whatever we're going to do is going to display the ODD symmetries of that action that we wrote before. It's just going to write this action in a way that the T-duality sort of symmetries will be visible. So here is the answer for this action. So it's a new action that has been written to describe the new physics and to make it duality invariant. Now, duality transformations are transformations in the indices m and n, capital M and N. And therefore, if you see good contractions in any term, and every term there is T-duality invariant, the sum of them is also T-duality invariant. And the only reason you have to work a little hard to obtain these terms there, and you see various things in there. You see the HMN. There's two derivatives in every term. There's the dilaton coupling to things. T-duality is manifest, and the peculiar form of these terms that you have there is such that you also have the gauge symmetry that includes diffeomorphisms and the B field gauge transformations. And we'll just show it in a second. So this time, the two parameters of gauge transformations also fit into an ODD multiplet. So between the D parameters of Kalb-Ramond and the D parameters of diffeomorphism, they build a psi M. And you could ask, what are the forms of these gauge transformations now that correspond to Kalb-Ramond transformations and everything? Remember, this field H, capital HMN, has the metric and has the Kalb-Ramond field everywhere mixed there. And the answer is that the gauge transformations that used to be normal Lie derivatives become what has been called generalized Lie derivatives. There's a formula there, and we'll say a little more about that formula, but that has a couple more terms than a normal Lie derivative would have. And then, if you look at the algebra of gauge transformations, you get a bracket. You do the commutator of two gauge transformations, you must get a gauge transformation with another parameter. In gravity, it would have been the Lie bracket, and here it is a new kind of bracket called the Courant bracket that was invented by Courant in the 90s, and Siegel's work sort of rediscovered that in the 93. And that bracket is written there. You know, here is something funny that is happening. In geometry, in Lie derivatives and everything, as we've said, the xi's always appear with an index up. And a derivative always appears with an index down. That or are their proper places. In generalized geometry, you now have a flat metric that allows you to lower this index and to raise this one. Something that, given that it's a constant metric and it sort of plays an auxiliary role, you can get away with this thing. And therefore, these formulas here show up having terms like the second term in this C bracket has some gauge parameter with the index up and one with the index down. You've used this new metric. Has the derivative with the index up. You've used the new metric. The first term is the Lie one. And Lie uses the right things, the ones that everybody loves. But in this double geometry or with the Courant bracket, you use this one. The Courant bracket is a fairly interesting object that deserves some explanation, but for now, this will be enough. So we've asked ourselves, where do these generalized Lie derivatives come from? And if you have an ordinary Lie derivative, it's associated with familiar coordinate transformations. This is how you transform a vector field in general relativity. And if you take an infinitesimal transformation, x prime being x minus a little psi m, you define the variation of the field A as the new field at the same point minus the old field at that same point. And a little calculation using the formula above shows that there's these two terms, and those are called the Lie derivative of AM. That's that derivative. It doesn't involve a connection. It doesn't involve anything. The indices are good. It's intrinsic. You can always take a Lie derivative. You don't even need the metric to take the Lie derivative. So you could ask, what is the full transformation, the analog of that top equation there, A prime equal this Jacobian times A, that gives you a generalized Lie derivative. I show here the generalized Lie derivative of an object with one index. It has two terms that are the familiar ones above, and then has an extra term that has this decay psi m with the indices flipped. It's almost like the generalized Lie derivative treats any index as a half covariant and half contravariant at the same time. It's a strange thing. So you can ask, if the Lie derivative is the infinitesimal form of the thing I wrote there, what is the form that gives this as the infinitesimal thing? And we found the result that this looks like double geometry, in that in order to transform a single index, you have to put this combination of Laplacians, of Jacobians. We've done a series of tests at that formula in this double geometry. It's funny, there's a sort of, it's a very peculiar formula and quite interesting. And there's lots of ways in which it could have gone wrong. And it works infinitesimally. That's the easiest part. Partial derivatives transform consistently. That's not obvious. A partial derivative should transform just like an object with an index down. The metric eta mn, which is a constant, is constant after you apply that transformation to both indices. Then if you look closely at these gauge transformations, these diffeomorphisms, they include coordinate transformations and B-field gauge transformations, and not much more. They are also consistent with viewing the large gauge transformations as exponentials of generalized Lie derivatives. Generalized Lie derivatives form a Lie algebra, even though the C bracket, this courant bracket, is not a Lie bracket. This is a remarkable thing. Actually, you know, the Lie bracket, the thing that we like the most about is a Lie algebra. You form the Jacobi identity and you get 0. With the courant bracket, or the C bracket, you form the Jacobi identity, you don't get 0, but you get something that doesn't transform the fields. This idea that psi tilde, if you have a Kalb-Ramond gauge parameter that is di of something, it doesn't generate a gauge transformation. If you look at this, it doesn't transform the B field. In generalized geometry, any psi m that is dm of something doesn't generate a diffeomorphism, doesn't generate anything. It's the analog statement. And therefore, the Jacobi identity, the Jacobi associator of parameters using the courant bracket should be 0, but it's not quite 0, but it's something trivial like that that doesn't generate transformation, so you barely make things work. Nevertheless, the courant bracket is not the Lie bracket, and the Lie bracket is the only form of diffeomorphisms that really associate. If you perform one after another, they associate. So when you start looking at these coordinate maps in detail with the C bracket, they don't quite associate at the level of coordinates. So they're very interesting and very surprising transformations. My last subject, as we move along, is going to be the sort of mystery of Riemann. And this is perhaps, for practical purposes, the most surprising and an important thing, and probably the thing that is going to imply where this field is going to go. If you look at the generalized geometry articles in the mathematics literature, there's no addressing of what the Riemann tensor is in generalized geometry. There's some discussion of things about Ricci and things like that, but not Riemann. And for some reason, because as I will argue now, in this geometry, there seems to exist no Riemann tensor, pretty much. Let's see what happens. In ordinary Riemannian geometry, people define the Riemann tensor, and if you studied general relativity first with Weinberg's book, which is excellent, it all comes from fairly sophisticated manipulations with indices and connections and everything. Mathematicians have a pretty formula to define the Riemann tensor. It's an object with 4 indices, so it can contract with 4 vectors, and that's the left-hand side there. And it's defined by those connections and covariant derivatives. So a relatively simple calculation shows that that kind of thing defines a tensor if you have a connection. So then the question is, how do you determine the connection? And the connection is determined typically in general relativity by the condition that the metric is covariantly constant and something called the torsion tensor vanishes. That determines the connection in terms of the metric, and that out comes the Riemann tensor. It's a very useful and nice definition. So what we were wondering is whether there is a similar definition in generalized geometry, which we have not found any such thing in the literature. This formula in blue is the formula we have found that actually works tensorially. This thing looks a little different. It sort of has a first line that looks similar, except that this bracket there has a letter D for Dorfman bracket, which for the purposes of this talk, the Dorfman bracket is really the Courant bracket up to a small modification, but it's morally the Courant bracket. And it should be like that, because if you take 2 generalized vectors and you make the Lie bracket, you don't get a generalized vector. Courant bracket is the thing for generalized geometry. So there's that thing there. And then you have this second line that sort of exchanges x, y, and zw, corresponds to a symmetry of the Riemann tensor that you probably all know, that you can exchange a pair of indices of them. And that doesn't come along for free in this theory. And unless you put this term, you cannot get it to work. And there's even a third correction term over there, where you sum over a complete basis of tangent vectors, an arbitrary one, and compute that. This formula is quite nice and defines a generalized tensor. So you say, okay, so you got your Riemann, but stop. We have to determine the connection still. How do you determine the connection? That second step fails. There's no way to determine the connection. This time the connection should be determined in terms of the fields of the theory. And the fields of the theory are H, Mn, and D, the dilaton. You impose that the metric is covariantly constant, that this metric is covariantly constant, that this metric is covariantly constant. You can put this. You require that this acts as a density. Fine. You can ask this 0 torsion, 0 generalized torsion, and still doesn't determine all the components of the connection. And in fact, you can pretty much prove, I don't think we've proven it, but we've tried it enough to convince ourselves, that the components that you can't determine of this connection are such that you cannot construct a formula for them in terms of the physical fields. It wouldn't transform right. So I don't think it's an accident or inventing more constraints. You just can't determine this connection. So what happens? You get this Riemann tensor that is partially determined, R, M, N, P, Q, and partially undetermined. When you take the trace to form Ricci, all the undetermined pieces disappear, and it's the Ricci of generalized geometry. If you take another trace, or trace in a different way more properly, you get the scalar curvature that I showed you. This scalar curvature that was here, that R comes out immediately. But there's no Riemann, as far as we know. And now, if you really think of what the geometry of string theory is all about, string theory contains what people call and make you think it's very sophisticated alpha prime corrections. The classical theory of strings is not just this R tensor of Einstein and that, but there's alpha prime corrections. There's terms with curvature squared, with curvature cubed, and they contain Riemann curvature squared. So the fact that we are not quite able to do a generalized Riemann properly suggests that something is still missing in this story. You somehow have to live without Riemann. And this probably is very important because there's a physical question here. There's definitely these corrections. We know they involve ordinary Riemann squared. And we know this duality symmetry should be preserved. That's string theory. So somehow you need to change the language here. Riemann doesn't quite exist anymore. I tend to believe that we're not going to find a very simple substitute for Riemann. I don't know what will happen, really, but Riemann, as we're familiar with, I don't think exists nor will exist. There's clues that the algebra of diffeomorphisms, that is the Lie algebra of Lie vector fields of gravity, maybe in string theory to make it compatible with T-duality also has alpha prime corrections. That would be fairly exotic as well. Something has to give. It may be that at the end of the day, you have this action that has, for string theory, that has square root of minus GR, and then it has square root of things, and Riemann squared. Well, it may happen that really the way this whole thing works is that this is not diffeomorphic invariant, and therefore if the diffeomorphisms, delta of G, have the normal thing plus alpha prime changes, it may be that the failure of this to be coordinate invariant in the large space is canceled by the variations of the original term. It's something that I think it's a great puzzle, and I really hope that someday I will be able to give a colloquium and a talk in which this mystery will be clarified. So that brings us to the end of the talk. Let me summarize the points we've made. The first one is that string gravity differs from normal Einstein gravity in that gravity field is always accompanied by a B field sourced by the strings and a dilaton that allows the existence of a duality symmetry. This symmetry can be made manifest in the language of double field theory that uses the idea that coordinates are doubled and extends key notions of generalized geometry. We have Courant brackets and generalized metrics, which were invented by these people, but the action was never quite written in terms of those quantities. There's an underlying geometry based on generalized Lie derivatives that suggests that somehow coordinate transformations are more exotic than we're familiar. Finally, there's a duality covariant definition of scalar curvature and Ricci curvature. There seems to be no well-defined duality covariant Riemann curvature. And this is a challenge, since low-energy actions use the Riemann tensor. And we hope that these ideas and remaining questions will teach us how Riemannian geometry is supposed to be changed. Thank you very much.
Okay, so we like to give students the first chance to ask questions. So if there's any students that have questions.
I was wondering if you've tried extending the definition of a connection.
If I had done what with a connection?
If you tried extending the definition of a connection.
You know, one could try to extend the definition of the connection. I've used this definition that sort of everybody uses. You have D. A connection, mathematicians, the way they write it, a little abstract. You have a vector field, and this acts on another vector field to give you a vector field. So the way we would define it is you say D along the vector field in the direction M, acting on the vector field on the dimension N, is equal to gamma M N K direction K. That is the usual definition in which basically we use a Christoffel connection with indices that are indices of the double coordinates. There's ways to put more symmetries, and just like you have this thing, you can put field binds, and define yet local Lorentz symmetries, the analog of local Lorentz transformations on the space-time, and uses yet another connection, the omega connection. But nevertheless, the difficulties seem to remain. So even though we can try to, the way we've done it is simply take the Christoffel connection and extend it to run over double coordinates. That's really the idea for us. You could put a spin connection, and that would be necessary for Fermi's. And as far as we can tell, you know, you don't solve the problem of Riemann with this so far. So if somebody will be maybe smarter or have the right idea, maybe they'll do it.
Any other student questions?
So does the generalized matrix contain the information of a dilaton?
No, the generalized metric does not contain the dilaton. The dilaton is another field, and it's a funny thing. Nevertheless, the geometry is so mixed up that the Ricci tensor is not a function of H alone, it's a function of H and D. You could try to put Weil factors of D into the generalized metric, and you know, I don't think anybody has gone further. We have a definition of the generalized metric. I gave you a definition, H as a function of things with G's and B's. So the generalized metric involves just G and B. Whether the alpha prime problem requires changing this definition or adding more terms that have dilatons or something is something we could try. I couldn't tell you. At this moment, it doesn't include the dilaton. Whether you need to include the dilaton in the generalized metric to somehow define, be able to do alpha prime, I don't know. But I emphasize that classical string theory has all the alpha prime corrections. So if what we're aiming is at the description of the classical geometry, which is a good thing to begin with, this problem has to be solved. And this is a very important thing, I think. Right.
So maybe we can throw it open to questions from everybody now. Students, of course, can continue to ask questions, but.
I was wondering if you've checked whether the generalized Ricci contains all the information that you would need from the standard Riemann.
For the standard what?
So I was wondering if the generalized Ricci contains the standard Riemann tensor.
No. It's, you know, just like the Ricci certainly doesn't have all the information of Riemann, except in very low dimensions. In low dimensions, I think up to 3 Ricci may have all of Riemann. The generalized Ricci doesn't have all the information of Riemann because Riemann has things that can't be determined. So Ricci is doing all what it should do. It's perfectly consistent. It's a generalized tensor. If you write the generalized Ricci equal to 0 equation, you find that it contains the ordinary Ricci being equal to 0 and the field equations for the B field and the field equations for the other things. So it's a fine Ricci. It's doing all what it's supposed to do, but it certainly doesn't contain any undetermined piece. So it really doesn't have the Riemann.
What I was wondering is not the generalized Riemann. Because that's not what you need for.
Yeah. No, it doesn't seem to contain either the ordinary Riemann in there. You see, the generalized Ricci comes from the generalized Riemann. And you could say, well, the generalized Riemann is not all determined, but maybe it does have all of the Riemann part determined. But we've checked that, and there are components of Riemann missing here. So the generalized Riemann is missing things, and it's missing enough of true Riemann.
So unlike Riemannian geometry, double geometry seems to have a preferred background metric, this eta mn. Is there any explanation?
It's not a background metric. You would call, in the usual way, we would call this the background metric, G and B and D, and this is a constant. It's some extra background metric,
right, it's a constant metric,
right,
that doesn't exist in Riemannian geometry.
Doesn't exist in Riemannian geometry.
Is there any expectation that should become ultimately dynamical and T-duality be gauged?
You know, it's hard to see. Let me say what people have said in the literature so far. Most people used to believe that the ODD transformations that have to do with this thing receive alpha prime corrections. So maybe, until we solve this problem, we don't know what really changes at the end of the day. So maybe alpha prime corrections will change this constant metric and make it do something else. And that would be reasonable if the T-duality transformations perhaps acquire alpha prime corrections. Nevertheless, all the work one has done with string theory and string field theory actually suggests that probably the T-duality transformations are not changed, and what is changed is diffeomorphism, the gauge invariance. Gauge invariances are a little less physical. They're very important. They're a little more subtle. They can be deformed in more ways. Global symmetries are very difficult to correct, I think. I don't know.
I have what might be a two-part question. Is the world sheet action for the string, can that be written in a manifestly T-duality invariant way using this geometry?
Good question. There's been many attempts to write manifestly T-duality invariant world sheet actions, and they're moderately satisfactory. I don't know very well the history. My colleague Chris Hall, that worked with me on this, knows the state of the art of it. As far as I know, there's no great action that everybody loves that is T-duality invariant manifestly on the world sheet. And part of the reason is that you have to double things. And once you start doubling things in first quantization, it's a little complicated. And And I think people have trouble. You would like to write the conformal field theory in a manifestly T-duality invariant way. And that seems to be hard, especially when writing vertex operators, because you need to double quite a lot of things. So,
but even the free string, if you could do that, then you could ask the question about the beta functions for the coupling, which should actually lead you to the right formulation of the
absolutely.
Riemann tensor and the alpha prime correction.
Absolutely. That would be a way to solve this problem. In a sense, however, the string field theory does that for you as well. The string field theory gives you the action for closed strings to all orders of alpha prime, and you just need to pick up the different pieces. In the case of the beta functions, they've been calculated to 2 loops, and there's been some work of people in a double formalism to do that. And the end result is that nobody has been able to get this right yet. I don't know.
We know that Einstein gravity, if you expand that near flat space-time, we have 2 physical propagating mode, elastic plus minus 2.
Yeah.
So I wonder for this string gravity, if you do the similar thing, expanding around the flat space-time, how many propagating mode do you have? Whether it's maybe that's related to experimental consequence of this.
Yeah, well, I think the answer to your question is basically, I'm going to give you the conventional answer. You have, in ordinary gravity, in 4 dimensions, the gravity field, G mu nu, in 4 dimensions, has 2 degrees of freedom. Freedom, indeed. You know, if you're in 10 dimensions, G mu nu has 35 degrees of freedom. Gravitons are a lot more complicated in 10 dimensions. And basically, the answer that we all believe is true is that in string theory, you know, the gravity is still gravity, so still has 2 degrees of freedom in 4 dimensions, but the B mu nu field actually has 1 degree of freedom in 4 dimensions, and the dilaton has 1 degree of freedom. So as far as we know, that doesn't change. The only difference is that those degrees of freedom of the metric now get supplemented by more degrees of freedom here. But the metric itself, at least to lowest order, is described by the Einstein's action. So its degrees of freedom really don't seem to change. There are funny things, however, with this HMN. I wrote for you a formula for HMN in terms of G and B. And very funny things happen. You can have G and B fields that go to infinity, that you would think are singular geometries, but H is finite. So if H is a better variable than G and B, this will have some meaning, not perhaps for degrees of freedom, but for the geometry itself.
But can I understand, so in the string gravity, there is actually 4 degree freedom at the low energy, which can propagating?
That's right.
I see. So then the question is that whether this additional degree freedom coming from the B and the psi have some sizable coupling to, say, to matters, then that may lead to some correction to Newton's gravity or things like that.
Right. Certainly, they have couplings to matter, and this one, if the couplings are too strong, tends to violate the conventional equivalence principle. It would be like Brans-Dicke gravity, and there are limits on the masses of this field and things like that. And these tend to give you axions in 4 dimensions. And therefore, they change things, but in an interesting way, for sure.
So maybe one more question?
It's a question about, it's a beautiful formalism that you presented, but there's something which I find puzzling, which is these constraints, that the fields have to satisfy.
Yes.
By that, that's okay, but the problem is that if I take the product of two fields, then, it doesn't satisfy it. So I wonder how much, and that's something which is unusual from the point of view of field theory.
Right.
I guess it makes the algebra of the fields non-associative. So I'm more how much of these problems are related to that?
Yeah, let me say a little bit of, let me clarify that point. I had to go a little fast on that. I said that all fields should be killed by this thing. Every field phi I should be killed by this. This is a constraint that exists even in string theory. You should adopt it in double field theory. Now, in full-fledged string theory, with all its excitation modes and everything, that's the only constraint that exists. And as you well said, that constraint doesn't imply that the product of two fields is equal to 0. This does not follow from this. This is a new constraint. But in the double field theory we're writing, we are imposing also that all products for all I and j, this is equal to 0. And that means that you're really is equivalent to saying that you're only keeping the massless degrees of freedom that we have originally in the conventional theory. So if you were to do, you see, full closed string theory is a double field theory, and it just has this constraint. But full string theory is fairly complicated, and what we said is we wanted to just isolate the gravity and not be bothered with the rest and see what's different in the gravity part. In order to do that, you need to impose this stronger constraint. So you reduce the theory, you truncate the theory to reduce it to this conventional degrees of freedom. So once you impose this, if you have 3 fields, it will still be 0 on any number of fields. This one now already follows, because with 2 derivatives, this is the last constraint you have. So at the end of the day, in the double field theory we have no problem with this constraint. It's everywhere implemented, doesn't involve anything very exotic. In string theory, full-fledged string theory, these are not imposed, and there are even more exotic things happening that the double field theory doesn't quite show us yet. So full string theory, it's still more exotic still.
Okay, let's thank the speaker again.
Thank you.
So next week we have the second Templeton Frontiers colloquium with Flavio Mercadi, and the high tea should be available in the bistro now.